So in the previous lecture, we started with the new unit operation, extraction, all right. And what we did there, we wanted you to be familiar with the equilateral triangular or equilateral graph here for the triangular system, okay. So because we said that we have three components, say A, B, C, and it's possible that all three components, they are miscible or partially miscible with each other. That means we can have a mixture which contains say A plus B, another mixture contains A plus C plus B, and the third component contains only B and C, all right. So in those cases, when we want to represent the mole fraction or weight fraction of one component in the mixture, then this kind of graph, equilateral graph, becomes quite handy here, all right. And we also said that you should buy this this kind of graph, or you can download from the internet and become familiar with this. Essentially, how these graphs are plotted depends upon on the property of this equilateral triangle. We said that if you choose any coordinate on any point in this equilateral triangle ABC and draw three perpendiculars, sum of all the perpendiculars are constant, means they're constant here. So which means you make use of this property. If you have 100%, say 100 moles, and all we are talking of distribution of A, B, and C in out of 100 moles. So if you choose one component here or locate one coordinate, then it contains say 60, 40, 60, 40, 0. That's also possible. And then we have 20, 80, 20. So the sum of all three components, weight fraction, is a constant here. So by making use of these properties, you have parallel lines along all the three sides, and then you have marked the axes with 0 to 100% for A, B, and C, etc. And then try to monitor how does the point move when you add two components. Okay. So let's just quickly go over this equilateral graph before we start. The first thing is the thermodynamics, phase diagram for ternary systems. Just like you had the phase diagram for liquid vapor, or you had the phase diagram or the solubility curve for the absorption system. Similarly, we have the phase diagram for ternary system in case of extractions. All right. So we continue our discussion with this extraction. All right. So we said that we have, say, equilateral triangle or graph. Traditionally, we put the solute C here on this apex, and we have A and B here. So if you choose any mole fraction here, any coordinate here, then we are trying to say that amount of C present. So C is 100% here, A is 100% here, and B is 100% here. So as you go in this direction, the amount of C increases from 0 on this horizontal axis, horizontal side AB, and it becomes 100%. So if you go here, you can note down what is the reading here on the graph paper. That reading will correspond to the amount of C. All right. Similarly, if we take a parallel line like this, line parallel to this BC, in which case A is 100% here and A is 0 on this line, and if you go in this direction and read the graph, say on AC, then 100 minus this reading or 1 minus this reading will tell you how much is the amount of A in this. All right. So A, must not forget that A increases in this direction, C increases in this direction. So you have to be careful how they have reported, the graph for this. Similarly, if you want to find out how much is the B in this components, of course 100 minus C and A will give you this. But at the same time, if you read this graph or read the line which is parallel to this AC, then whatever reading you have, that will represent the amount of B, the weight fractions. So B increases in this directions, and all this because of the rule of this equilateral, that summation of the three perpendiculars on the three sides is a constant. So if I choose here, then I draw the three perpendicular on the three sides. Sum of the three will also be constant, same as what we have the altitude, C to AB or A to BC or B to AC, etc. So making use of this property, one has this equilateral graph for extraction system here. All right. Then we said that if you choose, say, side AB again, and if you have, say, some point here M, you call it M, all it means the amount of A and B they have been added in this mixture, and the amount is proportional to the segment here. So again, you apply the mixing rule here. A by B will be equal to xm minus xb, so other side of this segment, over xa minus xm, all right, or minus xm plus xa to make it positive. So no C here, which means if we add certain amount of pure C and I draw a line like this, then I have the mixture, so I call it M here. So I have M and M prime here. So again, what is the amount of C in this? Now we have both A plus B plus C. So the fraction of C again will depend upon how much is the ratios of these two segments here. So again, we are applying a mixing rule for C added to this M dash to give us M here. All right. So this M dash is now, initially we had the mixture of A and B in that ratios, A is to B given here. So every time we are applying this mixing rule C, and then we have this mole fraction of C plus M dash mole fraction of this, and the resulting mixture mole fractions. So these are the two main things we discussed. This is different. Traditionally we have this XY graphs here, Y versus X. All right. So it's recommended that you become familiar with this graph. All right. So now what we start here is phase diagram. So essentially we are talking of now systems of 3 liquids. All right. And then if you go through the handbooks of extraction or even the textbook, they will talk of several types of systems here. We are concerned with mostly 2 types of system in our case. So we call it type 1, where we say that one pair is partially soluble. All right. Then we will discuss different type 2, a different system called type 2, in which we have 2 pairs partially soluble. All right. Of course, the first one is mostly common. So most of the example we will take in this course will be related to type 1. So again, let's try to understand, and that we have 3 components or 3 liquids, A plus B plus C. Let's say we have water, we have chloroform, and we have this acetone. Okay. So when we are saying that A, B, they are partially miscible, or B and C are partially miscible, all right, or A and C, they are completely miscible, then we should be able to plot accordingly on this ABC, on this equilateral graph, and it should be consistent with our earlier understanding of how to mark the coordinates on this plot here. So now let's assume that we are saying that A and B, all right, water and chloroform, they have limited solubility, or they are partially immiscible. So their solubilities are limited, or we can say that they are partially immiscible. Now everything is relative here. So let's try to understand that we are saying that water and chloroform, they are partially immiscible. But C, which is acetone, is completely miscible in A, and C is also completely miscible in B. Okay, which is true. Acetone and water, maybe under certain conditions, is completely miscible. Acetone is also completely miscible in chloroform. But when we mix water and chloroform, then we see that this small batch experiments they will get separated out like this. Okay, so we are using this word partially immiscible or completely miscible. Okay, and then we are trying to make a phase diagram here. So going back to this equilateral graphs, there are parallel lines to AB, parallel lines to this AC, parallel lines to this BC here. So now when A and B are limited, very partially limited, then we have the phase diagram like this. So let's first mark before we discuss further here, and we have the phase diagram like this. Okay. Now let's see, we say that A and C, they are completely miscible. So here if we choose any coordinates, you don't see any phase diagram. All it means, all mixtures of A and C, whether whatever proportion you use, large amount of C or large amount of B, if you add and mix, stir it, then you have say certain mixture composition XM, but you do not, you have a homogeneous solutions. All right. So you have a homogeneous solutions, or you have completely miscible. Similarly, if we add B and C and stir them properly, then we have a completely homogeneous solutions, or we have completely miscible system. On the other hand, if you mix A and B, and look at this, now we have this phase diagram. There will be a separations. So now here also we see some segments between A and L and K and B, in which we can say that the mixture of A and B, they are miscible. All right. So all it means, suppose I choose a mole fraction or weight fractions here XM, stir them and allow them to settle. We will have two phases. One phase will have contain some amount of A, mind you this is 100% here. So we have a large amount of A here, but very small amount of B in this. And we will have the second phase, in which we have very large amount of B, which is marked here K, and in which we have very small amount of A. So farther from this apex we have large amount of B, and farther from this we have large amount of A, and there is no C in this. So this is the meaning that A and B, they have limited solubilities. If I choose another say amount of this mole fractions or mixture here, and they allow them to settle. So when I say that when I have chosen XM1 and XM2, again you should go back and apply this mixing rule, that we are saying that the amount of A and amount of B, XM1 is different from amount of A and B in this XM2. But we are adding pure 100% A and we are adding pure 100% B here. Okay, so only the amount is ratio. So again the amount of A and B, you can apply this mixing rule. This would be equal to, let's say, XM1, so A by B minus whatever you have XB over XA minus XM1. All right. So the ratios of these two segments here. And if we choose any component here, now this will also contain A plus B plus C, given by what reading you read like this, what reading we read like this, and what reading we read like from here. So this contains A plus B plus C, except here we have this homogeneous mixture. So this is a phase diagram we have got like this. For ternary system A, B and C, we have homogeneous solutions mixture in this range. If you hatch it like this, and if we choose now a component or a mixture here of A plus B plus C within this region here and allow them to stir, now you will see a separation like this. There will be two phases. One phase will contains this amount coordinates given by this, another coordinates, another phase will contain the weight fraction of C given by this coordinate. Okay, so here we are talking of this phase separations. Here similarly, if we choose, let's say, A plus B C mixture of given by this coordinate, so certain amount of A, certain amount of B, certain amount of C, stir them and allow them to settle. All right. In that case, there will be phase separations, and experimentally if we measure, there will be two phases. One phase will contain so much amount of A, B and C, another phase will contain so much amount of A and B and C. All right. So let's again try to understand here this extractions. So if we recall, we started this before this extraction, we had a discussion on distillations. So we had liquid vapor, and of course we had only binary components. So when we had this phase diagram, liquid and vapor, and there if you choose fixed temperature and then you draw this horizontal line and you have a mixture of liquid and vapor, allow them to come to equilibrium, then we have this certain, there is separations. Vapor is rich in one component, liquid is rich in another component. But you have both A and plus B and A plus B in the liquid as well as this vapor phase. So that's a phase diagram. Beyond the upper limit, dew point, you have superheated vapor, one phase. Underneath this, you have another phase. In the regions of liquid and vapor, if you take any component, fixed temperatures, there will be separations. There will be A plus B in the vapor phase, A plus B in the liquid phase. So similar to that, we also have this solubility diagram for A plus B plus C. Now we have three components. All right. So now we have a phase diagram, which is it has marked certain regions. You have solute C, A, B, and then we said that if you choose any components of any mixture of A plus B plus C in certain regions above this phase diagram, stir them, so you are mixing, allow them to settle, there will still be one phase. However, if you choose a mixture which contains A plus B plus C within that region, stir them properly, leave them, allow them to settle, now you will see two phases. It's one phase lighter, underneath you will see another phase which is denser, high larger density, okay, and both phases will contain A plus B plus C, A plus B plus C. So if you recall earlier, we said that extract, and we have this now raffinate, okay. So both that there is a phase separations in certain regions in which we have a distribution of A plus B plus C. It's one thing that in one case C will be larger, another case we have C is smaller, in one case A is larger, another case you have B is larger, okay, but there is a phase separation. So here we are talking of system type 1 where two components A and C, they are partially miscible. So there is no phase diagram, there is no line there, right. Any mixture between A and C, in what proportion you mix it, no B, it's one phase. Choose C, mix with B, no matter what proportion you add them, you will get one phase. How much is the amount, right, that will be decided by how much amount you have added or the mole weight fractions you have started with. So suppose you choose now A and B. In that case, we are saying that A and B are partially solubles, or they have limited solubilities, or they are partially miscible. They are not completely miscible. In that case, if you choose A and B, say somewhere in 40%, 50%, or 60%, stir them, allow them to settle. Now there will be two phases. One phase will contain A plus B, A plus B. Second phase will also contain A plus B. There is no C because you are picking up the solutions on the horizontal axis of A and B. So C is 0 there. Now you have phase separation, A plus B here, A plus B here. Recall, liquid vapor, that type of argument we gave. Both A plus B, I choose here and here. In one phase, A will be larger, and another phase, B will be larger. Okay. So now let's replot here, and we'll give them the names like extract, raffinate. We will call them tie line, you will have the operating line, etc. So let's revisit this aspect of type 1. So we have type 1 system. Let us redraw this equilateral triangle, which is the graphical representation of three component system here. And we are saying that now we have this phase diagram, right. This phase diagram, it intersects the axis A and B, let's say at L, and say this K. And notice there is no intersection here. There is no intersections anywhere. All it means, anywhere if I choose, say, component coordinate H, this will contain A plus B plus C. We know how to read this. We'll take the reading here, we'll take the reading here, 100 minus this will give the other components. So from this, we have A plus B plus C. So I have this mixture of A plus B, I stirred them, and then I allow them to settle. I will just see one phase, and this phase will contain A plus B plus C. So all miscible. I choose another component here. So it has certain percentage of A plus B plus C, stir them, allow them to settle, still there will be one phase. So this is one phase system here. It's all one phase. Because A and C, they are completely miscible here, B and C, they are completely miscible. Now let's look at the horizontal line here of this coordinate, triangle ABC. Now here if I choose a component of A and plus B, a mixture of A and B, in that ratios, certain ratios giving this mixture density, mixture mole fraction or weight fraction as Xm. Now I take this AB, I stir them, allow them to settle. Now there will be two phases. Both phases will contain A plus B. this phase will also contain A plus B, but in one case A will be larger, another case B will be larger. So recall our analogy between liquid and vapor. With the top product, say vapor, bottom product we had the liquid, both contains A plus B, but in one case A is larger, another case B is larger, bottom product. So here we have the same story. If we take this, allow them to settle, now I have L and K represented by this. This guy closer to this apex, so it's rich in A. This coordinate closer to B, it's rich in B. So we have 100% A, this apex 100% B here, and allow them to settle. Now we have this rich in. So this is nothing but a tie line. All right, this tie line is very close or very similar to this liquid vapor tie line. You fix the temperature, then the mole fractions of vapor and the mole fractions of liquid, they are fixed. Fix the temperature here, mole fraction of A and B in this, mole fraction of A and B in this are fixed. Start with another mixture, stir them, settle, you will get back the same results. They will get back L and K. Start any mixture here, allow them to settle, equilibrium, you have the fixed mole fraction. Start with here, allow them to settle at this temperature, equilibrium, you get the fixed result. So we have this tie line essentially. Now what happens here? Suppose I choose a component this. So it's another experiment. Now I am choosing coordinate where I have 3A plus B plus C. So I have chosen 3 components, A plus B plus C, water, chloroform and acetone, mix them, allow them to settle. Now if you do this experiment, now there will be 2 phases, just like here. So here also we have 2 phases, except one phase, both the phases will contain now A plus B plus C. Here C was 0, but now you have C here. So that means if there is a phase separations, equilibrium, there is a tie line. So now we have tie line like this, and we give them the name here. One phase which is rich in A, we are calling it raffinate. So this is raffinate. This any point here will be called as raffinate phase. Okay, because this contains large amount of A and small amount of C here. Similarly, this side, this line, any point here, we'll call them as extract, which means we have B is acting as a solvent, and this contains larger amount of C than this. So we have the tie line positive with the positive slope. Let's try to understand the meaning of this. A we are using as a feed, C is a solute, and B is a solvent. Take any mixture of A plus B plus C anywhere within this region, stir it. So extraction always consists of 2 steps. One is mixing and one is settling. So you represent like a CSTR reactor, and here you have very simple settler, no mixing. So we have taken this, we have mixed them, A plus B plus C, temperature is fixed, allow them to settle, we get 2 phases, raffinate and extract. Raffinate phase contains certain amount of C, which is smaller than what we have in case of extract. That's what we will also expect. So this vapor phase and liquid phase, you can make the same analogy. More volatile has gone here, less volatile has gone here. So one which was more soluble in this B as a solvent has gone here, and it's less. So there is a phase separations. Okay, you can call them as R, and we call this mark as E. R for raffinate and E for extract. This is your X, M or M point. Okay, let's take another point here. So we have another mixtures, allow them to mix them first, settle them. You get another tie lines, not necessarily with the same slope. So again we have another R, we have another extract. Typically there is a point here called P, which denotes as plate ELI. So it's a plate point. This is a point where now there is no tie line. All right. So this is a limit of this separation here. So we have this line here. After this, there is another tie line here. Okay. So at every time below this point P, you will see that this extract phase has larger mole weight fractions than this raffinate. Beyond this P points, now tie line slope changes, and then Y, this weight fraction in this raffinate is now larger than this extract. We'll come back to this. But the idea here is about this two-phase system, heterogeneous system. All right. Unlike in this range, we have one phase system right here. Even here, if you choose a component of A and B, mix them, allow them to settle, there is no phase separation. Phase separation occurs in this range. That's your solubility curve. All right. If I choose, let's say, another M here and allow them to mix them, allow them to settle, again you will get the same weight fraction R and E. This is equivalent, very much equivalent to just the liquid and vapor diagram which we discussed earlier. So we have L and V, choose this temperature, you have vapor phase and liquid phase composition fixed, or you start with some mixed feed here and then at this temperature, if they give them equilibrium, allow them to come to equilibrium, you have this is fixed here. I choose another weight feed here in some batch experiment. You can allow them to settle, I get the same L and V. It's only the amount of L and V will be different. It's only the amount which is different here, depending upon the ratios of the two segments across this mixture point, M or M. So we have the same situation here. There are tie lines, the phase, and there is a tie line like this. This is E here, extract, we have raffinate. We have A, we have B, we have C. It's closer to this A is larger here, B is smaller here, okay, and C is smaller than in extract phase. That's what you will expect. Large amount of solvent has taken most of the solute, much larger than what you have here. Similarly, you have another tie line, different slope, different slope. You have all R, you have all extract, till you have this P platelet points at which the slope now changes. Now you have raffinate phase, extract phase composition is smaller than this raffinate phase, which means if you take these projections and plot just like Y versus X. All right, so now we are going from this triangular diagram to this Cartesian coordinate system with Y and X. So just take this Y here, we call it extract with the weight fraction Y and all the raffinate as extract. This is a P plate points and plot Y versus X with this as a 45-degree line. You will expect the curve like this. This will be the most general. So that means beyond P now, X has become, this is Y larger than X, Y larger than the X. Right now you will start seeing things getting leveled here below this. Okay, so this is now your P point, platelet point. Excuse me. Beyond certain point, you will see the tie line slope have changed. So the amount of Y has started becoming less and less. So we have this Y versus X diagram. For our understanding, we can call it Y versus X as distribution coefficient. At the plate points, there is no separation, so it's always greater than 1 above this 45-degree lines. Below this P, we have there's no phase separations here. All right, we're calling this, let's just label it between R and between this point and this point. This is the raffinate phase. So it's a raffinate. It's rich in A. Essentially, you have a feed, right? And you have small amount of C now, okay, and very small amount of B also. So it's a 3-component system, except it's rich in A. A small amount of C because most of the C has gone into this extract phase. So we are comparing 1 to 1. So it has gone to extract phase. That also contains A, B, and C, except it's larger amount of solvents closer to this apex. So large amount of solvents, C is larger. See, this is closer to the C, closer than this point. So anywhere tie line, this is closer than this. Y is greater than X, except beyond this platelet points. Now the slope start decreasing. So if the slope like this, now you like this, slowly and slowly, beyond this P, now slope starts decreasing. Okay. So it's closer towards C here. So we have B plus C, away from A. So very little amount of A here. When we say C is large, is we are trying to compare with this C in this extra raffinate phase. Okay, and anywhere if we choose M, we are saying that this is XM. We have mixed them, we have settled, allow them to settle. Now there is R and phase separations. Okay, for any of this R and E, we can also apply mixing rule. So we have essentially R and E. If you take this M, right, and you want to write down how much is the amount of extract and how much amount of raffinate is formed, still you apply R plus E as M, R, XR, E, you have XE. Generally we like to use Y for the extract phase. Nonetheless, this is Y into XM. Okay, so you can write down the amount of raffinate over extract, applying this tie rule. So R by E, you should be able to show that this is XE minus XM, and extract, this is XM minus XR. So again we have the same tie rule, material balance, all we are trying to distribute here. So extract, fundamentally it consists of two steps. One is mixing and one is just settle. And when we settle, there is a phase separations. Extract phase and raffinate, which is nothing but we call it residue also sometimes. This extract will contain, we have extracted using a solvent, right? And raffinate is your feed, which will also contain a solvent, but C is smaller here. C is larger here. Some A will also go here. All right, this is A here, and some solvent B will also go here. Okay. So this is your introduction to your phase diagram for extractions. Fundamentally, of course, the two are different operations. One is absorption we had, then we had distillations, then we have this extraction. But the approach in all these three cases is the same. First, we have to understand the thermodynamics. In case of absorptions, it's a Henry's law, solubility, that decides how Y and X, that is how the solute is distributed between the two phase, air, gas phase, and in water. In case of distillations, we have two phases, liquid and vapor, and now both A and B, they are distributed. One which was more volatile went to the vapor phase, one which was less volatile went to the liquid phase. But here also we have phase separations. Now the mechanism is determined by relative volatility. In extraction is also we have phase separations, but now we are talking of distributions, solubility, right? And we have now three components, A plus B plus C. One we call it as a feed, all right. One is a solvent, and the C is your solute. So if feed is contaminated with some C, maybe there is no B, that's also possible in one limit. So we have A and C. So recall our triangular diagram, A, B, and C. No B there, just feed, it contains some C, so we are somewhere here. Where is the amount? That depends upon, where is the coordinate? That depends upon the amount of A and C which you have added. We want to remove C, so we add a solvent, pure solvent. It may not be pure, it may contain some amount of C, it's possible. It may also contain some amount of A, but the most simplest case would be that we have a pure amount of solvent. So we are on the apex B, 100% B. You mix the two. So essentially you are mixing in a beaker where you have A and C. So hypothetically you have a mixture where the mole fraction is given by that M. So you connect M to this B here. Apply the mixing rule again. Somewhere on this straight line you will get XM mixing, mole for weight fractions, right? Where will be the location? You write down your material balance, write down your feed balance, species balance in terms of the weight fractions to find out how much is the amount of you have the solvent, how much amount of you have the feed, and you have the solute. So now when you add like this, stir them, mix them, there is a phase separations. You have the tie line, very similar to what we had in case of liquid paper. So now you have to rely on this phase diagram. All this phase diagram for all the ternary system or the binary system, they are available in the textbook, in the handbook. There is several types of systems you have. Trebol textbook. You can also go to the other book by Datta and look for this type of phase diagram or the solubility diagram. So essentially now you have separations, and all we are saying that when we have the separations, one is called raffinate phase, one is called extract phase. So you are extracting it. So raffinate is nothing but your residue. Feed contains now a small amount of C. That's what he wanted. He wanted to remove C from feed. So you have F A plus C. So C will be very small there. But there is a possibility that there will be some carryover of solvent also. So you have A plus B plus C. You have the extract phase where most of C has gone there. At least in one stage, larger amount of C has gone there. But there will be some carryover of feed as well. So it's still there, you have A plus B plus C. But C is larger, A is smaller, and B is larger because that's the solvent there. Again, you apply the mixing rule, you have the tie line. All these three lines will lie on the tie line, the straight line. Okay. You have some other mixed compositions, you have another tie line. So there is a phase separation for depending upon what weight fraction we choose here. We go to the point P plate. There you have no separations. All the tie lines have reduced to zero length. Okay. And when you take the projections of all this phase diagram on YX, again you get a Y versus X solubility curve here. All right. So for separations, Y versus X diagram should be over 45-degree line, or the distribution coefficient Y over X or Y star over X should be larger than 1. All right. So now let us understand this temperature effects. Very similar to the earlier case also. Whenever we have this solubility, then they become a strong function of temperature. So whatever phase diagram we have, we are saying that two mixtures like A and B, they are partially miscible. A and C are completely miscible. But it's possible that at high temperatures, we will have larger and larger solubilities for most of the systems, and this phase diagram will actually shrink. So let's draw this here. So we are drawing this qualitatively. You can go through the book, textbook, to see exact locations or exact numbers for the different systems. So again we have A, B, and C. So at certain temperature we have drawn this phase diagram. So this is at one temperature. Here we are saying that A and C completely miscible, B and C completely miscible. This is the range. This is the region where we have this homogeneous system including here and here, and on this when we have A and B, then they are partially miscible. So they have limited solubility. So you will expect that when you increase the temperature, then this region will shrink here. So now you can see that now the region has increased, and this region of partially miscibility has decreased here. So this point moves towards this point moves towards this. You have large amount of B here. Earlier you have very large amount of A, small amount of B. Now this locus moves, this point moves this way, and this point moves this way. Similarly, we have at the higher temperature, this will shrink, and it's possible that at a very last temperature, only the bottom line is that A, B, and C, the three components, must not decompose. So at a very last temperature, it's possible that we have now completely miscible, and this point will vanish. So we have this increasing temperature. And at this point, now we have completely soluble. So essentially, all phase diagram will vanish, and we have perfectly homogeneous solutions of A and B and C. So this is what you will also expect here. All right. So this is about the temperature effects. Okay, and we are discussing about this type 1 system. Now let's discuss this type 2 system. Now again here we have systems of 3 liquids, same as before, except now we are saying that 2 pairs are partially soluble. Alright, so when we are saying 2 pairs are partially soluble, let's again look at A, B, C. As an example, let's say we have chlorobenzene, we have water, and we have this ethyl acetate. Petroleum industry is one of the industries where you will get several of such examples. Okay, so now we are saying that A and C, they are soluble, which is true. Chlorobenzene is soluble in ethyl acetate. Okay, again it depends upon the temperature, but let's say that normal temperature, room temperature, we have this chlorobenzene soluble in methyl acetate. But A and B, they are partially soluble, and B and C, they are also partially soluble. So we are talking of 2 pairs which are partially soluble. That's a type 2 system. Okay, and more important here is to draw this type of phase diagram or understand what we mean by 2 pairs being soluble. So again we start with the equilateral graph. We have A, B and C. Now we are saying that if A and C, they are completely soluble, so we do not have any phase separation here. But B and C as well as A and B, they are partially soluble. So you will expect a phase diagram like this. Okay, let's again try to understand what we are saying here. There is a region over which A and B, they are partially soluble. So any mixture between this and this line here, if you mark it L and say K, you allow them to settle, they will separate. Okay, here you have homogeneous mixture of A and B. Here you have homogeneous mixture of A and B. Similarly, if you take B and C, no amount of A here along this side here, then there is a region at which, over which if you choose any weight fraction, any mixture of B and C and allow them to settle, they will separate into this. So we have 2 pairs of B and C which are partially soluble. This is what the meaning of partially soluble is. Here you have large amount of C, here you have large amount of B. If B and C, they become totally soluble, then you will not see any phase diagram here. So there will be a curve like this. See, no intersection of this phase diagram over this line B and C. Alright, so this is the meaning of 2 pairs partially soluble as we have represented it on this curve here. Okay, let's redraw again. So we have A, B and C. We have this phase, we call it H. Just mark a line here, say this L. Okay, and very similar to the previous case, now we choose any mixture here which will contain A plus B plus C, all 3. Allow them to settle, there will be a tie line, or there are just separations. Tie line represents equilibrium, so there will be a tie line. This phase, we call it R, raffinate. This phase we call it extract, say E. Alright, so again if you choose M, mark this coordinate as M and say that you have reached the equilibrium, raffinate will contain certain mole fraction, say XR of C. The extract will contain certain weight fractions of C again here in this. Okay, if you choose any other mole fractions here, again there will be allow them to settle, there will be a tie line, then need not be parallel. Again you can apply the mixing rule to obtain how much is the amount of R and how much is the amount of extract here. If I choose here, all it means is still there is a tie line, except there is no amount of C here. If I choose any amount here, any mixture of B and C, all it means there is no A here, and we have this tie line. So there is a tie line like this, like this, like this, which represents equilibrium between the raffinate phase and extract phase. One can plot this. You can take actually projections. So if you take a projection, suppose this is a 45-degree line here, and we have this XR, and let's say this E is represented by XE. All right, so you are reading it all the time. It's a C. You are reading it from this graph line like this, parallel, which goes through this, which goes through this. So now if you take this projections along this, so 45-degree line, and take C here. All right, so one can show that you will get one coordinate. So again, you do the same thing what we did earlier when you have taken the projections like this and extend this component here. So this will represent your E and R. So this is coordinate which comes from here is XR, and what you are reading here is your Y. Okay, so this YE is extract phase compositions, XR is your raffinate, and you get this line. Similarly, take any other points, any other tie lines, and take the extend it here, take a projections here, take its corresponding extract phase. Okay, mark this point here, and then you draw this line. You have a solubility curve. Okay, so similarly, so essentially we have plotted same equilibrium curve. Now we have plotted as Y versus X here. Okay, similarly, all of this we can discuss about this effect of temperature. If you increase the temperature, it's possible that P and C maybe become solubilized at high temperatures. In that case, you will expect there will be phase separations. So we have A, B, and C. Alright, it's possible that at certain temperature A and B, maybe they become miscible. So all this phase diagram, now they will change like this. Alright, so this region has now decreased. So again, you can go through the textbook to see that you have different types of system and you have different effect of temperature. Now what we do here before we go to the next stage, of course we said that for A plus B plus C 3 system binary ternary systems, we require an equilateral triangle. But we must not forget that if we fix the amount of A and B or weight fraction of A and B, then the C is fixed 100 minus A and B. Or if we fix the amount of B and C, the third component is fixed. So there are other coordinate systems, including this rectangular systems, which can also be used to represent this ternary system. Of course, all three values you won't be able to read directly. Like in case of equilateral triangles, you have any coordinates, you read the readings from all three sides of equilateral triangle to obtain this A and B and C. But if you have this coordinate system, traditionally you have this Cartesian coordinate system, there also you can work on mole fractions, just two component system here. The third will be 100 minus this. So that's also quite frequently used, and we will just draw qualitatively here other type of coordinate system. So suppose we have this A, B, and C. A, B, and here you have C. So let's say this is a phase diagram. You have say certain tie lines like this, extract, and let's say this is your raffinate. So we have XR and we have this XE or YE. Generally for extract you use Y nomenclatures. Here you have XM. Okay, one can also take a projections. Suppose we have this now. You can plot different ways here. So now we plot weight fraction of B, because that's the amount of solvent one uses. So generally the standard problems would be that you have A, it contains some amount of C, and you are adding B solvent. So same A plus B and C, one can also represent in a different way. You have got 90-degree perpendicular system here. So you're plotting weight fraction of B on the X system. O, B, so B would be here 100%, or 1 and 0 here. Same plot. Now if you take a projections of E, you take this projection of this R, you will also get a phase diagram like this. So what we essentially are plotting amount of C. So this is 1 here. So this is the most common way, another common way of plotting it. Of course, here if we choose any coordinate, we can read all the 3 readings here. But the most important is that what is the amount of contaminant solute you have in the system and how much amount of solvent you are adding it to remove this. So generally on the x-axis, if you plot weight fraction of B, and here you plot weight fraction of C here, okay, the A would be 1 minus B and C anywhere. So we don't need to plot exactly on this equilateral triangle. So still you have the phase diagram, you have a tie line, so you have extended this here as extract. You take this, definite all this all the way till here, you have this the tie line. You have this M as this. So this will also work as a representation of this extraction system with this as raffinate phase here. Here you will have extract phase, you will have XR, you have XC, except now the amount of A we have to calculate from 1 minus whatever B you have, whatever you have C here. So the two are quite analogous. There is very similarity here. Here there is a convenience of calculating or readings or A, B and C directly. Here of course one has to obtain the amount of A by simply subtracting B and C. So essentially we just plot weight fraction of B and weight fraction of C because we know that A will be 1 minus this. So both of them are equally popular, and most of the textbooks they give importance to both of the different style of plotting here. Okay, so this was our introductions to two different type of systems we have. In one case C is soluble in both A and B, but A and B are immiscible or partially soluble, or they have limited solubilities, so that we call it type 1. Then we discussed type 2, which had 2 pairs insoluble. So we had a different type of phase diagram. Again, as we said earlier, there are different types of systems and all kinds of possibilities possible, especially when you notice or when you observe this temperature effects. Okay, so in this course we will take a simple case of type 1 or type 2 systems, and we will see apply the mixing rule, apply this equilibrium phase diagram to determine how much is the amount of solvent is required to remove, say, this amount of C from, say, 10% to 0.1%. All right. So now we are talking of stage operations. So far we had thermodynamics, all right. And now we are talking of this stage operations. Okay. So let's continue with this operations. So very simple, big single stage contact. So we have single stage contact. So you have stage 1. Let's say we have F, composition is XF. Let's say for our simplicity that we have A plus C only. So there is no B, although we can extend our discussion to say that this also contains B. So now we have A plus C. C is a solute. We want to remove this solute by bringing B, which is a solvent. It has mole fractions YS. This solvent can also be pure. All right. This may also contain some amount of A and C as well. So all possibilities are there. For simplicity, let's say that we have very small amount of A or C in this. So it's very closer to this apex B of this equilibrium triangle. Now we allow them to settle. So they mix first. All right. Then you allow them to settle. So generally this is stage 1. Experimentally you will have to show with the 2 unit operations. In one case you have mixing, take out this product and then allow them to settle. So when you do this, now there is a phase separations. You have raffinate phase 1, we have this X1, we have extract phase, we have Y1, and they are in equilibrium. So single stage operations. We come to this ABC diagram, the equilibrium triangle. A, B, C. We look at the handbook for the system. We have this phase diagram. There is a P, platelet point. And now we have to mark all these points. So we have F, A plus C. So this A and C, that means F is here. All right. There is no B here. Although in principle it's possible that we can have feed here also. So all possibilities are there. For simplicity, let's assume that feed contains only A and C. Now we add the solvent. We want to remove the C from this. We can add a pure solvent, 100%, or we can have some small amount of solvent. ys. So that possibility is also there. So now I have added these two, settle, stirred them, and then allowed them to settle. First thing is that if you connect this straight line, the mixture has to fall on this, because it's a mixing rule. F plus B equals R plus E, alright, or F plus solvent equals R plus E. You have R1, E1 and S. So you get XM. This is the first unit operation for this. Once you allow them to settle, now you have this tie line. This represents this tie line. So you have R1 raffinate and you have extract here. All you have done, now we can write F plus S1, say amount of solvent required, S1 here instead of B, will equal to M1, which is this. So that's one into operations. But when you allow them to settle, now you have E1 plus R1. And you have species balance. F into XF plus S1 into YS will be equal to M1 into XM. So that's a mixing. But when you allow them to settle, they will separate as E1, Y1 plus X1 into R1. So we have similar situation. One mixing rule we are applying in two contexts. One is mixing of feed with the solvent, and then separation between R and E. All of this, they have to intersect at one line, because this M satisfies this mixing as well as M satisfies this separations, and that's the tie line. Y1 and X1, they are connected with the equilibrium or some equilibrium curve here. So this becomes our basis for our discussion for stage operations. All right. So what we have done, we started with this course extractions. First thing was the familiarity with this equilateral triangle, the graph. How do we represent ternary systems A, B, and C? That's number one. Number two, we talked of thermodynamics, the way we talked of thermodynamics in absorption and distillation. So we have this phase diagram. Phase diagram depends upon what type of systems we have. System 1, system 2, which two of them are partially miscible, which two components are partially immiscible, etc. Then we talked of this mixing rule, okay, which we apply in both cases. We are mixing feed with the solvent, so we have one mixing rule. And now we talk of separations, tie line, equilibrium, where we separate into extract and the raffinate phase. Okay, so the same common principle what we did, if you remember the third or fourth lectures, when we talked of the cascades, and we said that cascades, they could be in co-current, cross current, or counter current. We are making the same analogy. Earlier that example was for binary system. Now we are doing actually for ternary systems. But our principle, our approach is the same. You have to start with the thermodynamics, certain phase diagram, then make a material balance, make a species balance, see how much amount of, applying the tie rules, what amount of component is separated, or what amount of extract and the raffinate they are formed here. All right. So next class we will continue with the multiple stage contact.